for being here today. Today it's my pleasure to introduce Jason Kim, who will be defending his thesis, hopefully successfully. So, if I can say something about Jason, is that he has always been quite eager to learn and to connect things and try new things. Some days a bit too eager, but that's been good overall. And just to kind of illustrate this, even when he was trying his PhD, Jason actually contacted me before he arrived to see if he could start working in the summer before he arrived. So he actually started working in my lab the summer before he officially started his PhD and continued there for 7 years. So I can say over the time he's done really great work. He has obtained a lot of results. And most of his work has focused on the generation of light or quantum states of light that can be tuned around resonance for applications in quantum sensing. And today, Jason's going to tell us a bit about how those work and the great results that he has obtained so far. So Jason, please go ahead.
So my name is Jason Kim. I was at the University of Oklahoma for 7 years at the Polarization Quantum Optics lab. And I was lucky to be able to be part of the transformation from the physics department to the Center for Quantum Research and Technology. I was here for 3 years. And throughout 3 years, I've seen a lot of changes. We double and triple the size of the faculties. And we are becoming a leader of the Quantum Institute. So I feel really lucky to be part of this transformation. So today can be a meaningful day. It can be my last day of the PhD program and the first day of the new journey from the University of Oklahoma and Center for Quantum Research and Technology. So I'm really excited and pleased to speak with you about my work on generation of the atomic resonance squeeze light and how this can be applied to the quantum information sciences. So squeeze state of light is a quantum state of light which have a reduced noise property. And due to this property, it has been used to enhance the optical devices such as optical interferometer. So this idea was first proposed in 1981 by Cave, and he is proposing using the squeeze light in one of the port of the interferometer to enhance the sensitivity of this device to measure the gravitational wave from the universe. Now this idea is integrated to the LIGO, and then now using the squeeze light, LIGO is measuring the signal from the universe. And in our lab, we try to extend this idea to different devices. One of the applications is plasma sensor, which is biochemical detector. And in our lab, we also try to enhance the optical imaging system. So my work is focusing on enhancing these optical devices to atomic devices, because atomic devices show extreme sensitivity for their environment, such as atomic clock here. This is used into the, now this is atomic clock. Sorry, there's some kind of thing. And now this is integrated to like satellites and try to optimize the GPS and signal. And also some of the atomic clocks are used into the financial trade to optimize their trading strategies. So therefore, there's a lot of interest to enhance the optical clock and atomic devices. And my work is try to focus on how we can use the squeeze light to enhance these optical devices. This work was proposed, some of the work was proposed to enhance the optical interferometer. And they already showed us some demonstration of enhancing the atomic magnetometer and spectroscopy. But to do that, we need to have efficient interaction between atom and light. So then we need to generate the resonance squeeze light. So my work is focusing on the generation of the resonance squeeze light. First, I will talk about what is quantum light and how we generate the squeeze light. After that, I will talk about my work to generate the resonance squeeze light and how we increase the frequency tunability of the squeeze light. And then I will explain how this can be applicable for the quantum information science and come to the conclusion. So you can see there's a symbol here. Since it's like 45 to 50 minutes talk, this will kind of guide you where you are in this presentation. So before I go into the detail, let's talk about a little bit of history. So Einstein discovered the photoelectric effect by assuming that light is particle and light at the same time. So using that, he got a Nobel Prize. And after that, Heisenberg find out some kind of relationship between the uncertainty of the momentum and uncertainty of the position of the quantum particle, and he also got the Nobel Prize. Now, because of this Heisenberg uncertainty principle and Einstein, we can kind of explain about the quantum particle. So for example, if you try to explain about the classical particle, like let's say duck, and into some kind of diagram here, this is called phase-space diagram. And phase-space diagram is x-axis is the position, and y-axis is momentum. In this case, when you try to represent a classical object, we can kind of think as just a dot, and there's a 4, and then 4 for the momentum. But quantum mechanics, because Heisenberg said the principle, we don't really have a well-defined position and momentum anymore. That's why we have to kind of introduce some noise around that point. So now when you try to represent the quantum particle, we have to put some noise into the phase space diagram. Keep that in your mind. Let's go a little bit deeper about the mathematical description of the quantum light. So try to explain the quantum light, we need to quantize the system. So we can assume that, let's say we have a cavity, some kind of like space, and then we put the light in there. And
when you say noise, you mean quantum uncertainty?
Yes, uncertainty. So let's say we try to explain the electric field, and we can quantize the electric field by using the raising and lowering operator, which is that we are adding a photon inside the cavity and removing the photon inside the cavity. In this case, you can see the volume is here, and the frequency of the light is in the omega. So since it's electric field, we can kind of separate them by the real part and imaginary part. And we are doing, we can see that X is the real part of the electric field and Y is the imaginary part of the electric field. We are doing this one and we call this one as a quadrature. We are doing this because this is something related to measurable quantity, such as amplitude and phase. I will talk about a little bit later how this is really related to amplitude and phase, but you can just think as X and Y is something we can measure in the experiment. So because we know the commutation relationship of the A and A vega, we can also find the commutation relationship for the amplitude and phase. And we can drive the uncertainty relationship, so then we can find the uncertainty of the amplitude and uncertainty of the phase. The product of these two properties have to be equal to greater than equal to certain number. So for example, in the vacuum state, let's say we get rid of all the photon inside of the cavity, we can say that the mean value, and then we can calculate and say the mean value, and then the mean value of the amplitude and phase is equal to 0, because we don't really have any amplitude. But when you work on the math, we will find that the uncertainty is still exists there. So even though we get rid of all the photon, there is still uncertainty associated with the vacuum. And this is called vacuum state. And you can see that the mean value is equal to 0 in the phase space diagram, but still because of the uncertainty, you can see something like uncertain region around that mean value. And this is in the number basis, like if we show how many photon in there, we can represent this as a 0 cat, which is nothing in there. And this noise associated with this vacuum noise is called quantum noise limit. Yes, this is called quantum noise limit. So, like this is explanation of the vacuum field. But let's say if you try to explain the laser light, we need to have some kind of amplitude and phase. So here, let's say if you have a really nice laser, it doesn't really introduce any fluctuation when you amplify the light, then we can kind of think as moving the vacuum noise to a certain amplitude. And this can be done by the displacement operation. And then you can see that alpha is representing how much we are moving this block of the sphere in here. And this is called coherent state, and you can see that we are moving the displacement of the vacuum, and we can represent with the alpha. In here, it's a little bit clear why this is related to amplitude and phase, because let's say if you rotate our axis and then align to our amplitude axis. In this case, the projection of this circle in this new x-axis is representing the uncertainty of the amplitude, and when we have a large amplitude, then we can assume that this uncertainty of the angle, which is uncertainty of the phase, is the projection of the y, which means that uncertainty of the phase is related to uncertainty of the y. That's why we can kind of refer as x and y as amplitude and phase noise. So this is not really familiar with most of people when you're thinking of the electric field. When you do the time evolution, this will be a little bit more familiar to you. So let's say if you project into the x-axis, which means that we are looking at just amplitude, and do the time evolution, then you will see what you know about the electric field. You see the oscillation of the amplitude, and in classical mechanics, you might know that you might think that this will be just well-defined amplitude and phase. That's why this red line represents the classical description of the electric field. You have a well-defined electric field, amplitude and phase. However, because of the quantum uncertainty, like a quantum noise limit, this noise coupled into our electric field, now we don't really have well-defined amplitude or phase anymore. That's why there's a noise associated with our measurement. So Korean state with a simple calculation can be represented into the number basis. And this one, let's say you have a laser light and you measure with a photon counter. And then you just count number of the photon with a given time. In this case, you can calculate it and you can find that this kind of distribution. And this distribution is Poissonian distribution. And one of the interesting about the Poissonian distribution is that the mean value and variance is equal to each other. But another interesting thing about the Poissonian distribution is this is come from the random and independent event. So let's say, like for example, if you have a bucket of shot, pour it to the ground and see number of the shots hitting on the ground, that will give you the Poissonian distribution. So then, which means that the particle nature of the light is consist with the Poissonian distribution, which is the behavior of the shots. So then the particle nature gives the quantum noise limit. So let's say if you want to show the quantum nature of the light, we need to squeeze the light. And not the physical squeezing like squeezing the dog, more like a squeezing into the phase space diagram. So let's say if you squeeze the light in the phase space diagram, so in here, then you can see that one of the noise quadrature, like uncertainty is lower than the quantum noise limit, but the other uncertainty is larger than the quantum noise limit. But we still hold the uncertainty principle. In this case, this is called squeeze state of light, where the one of the quadrature is lower than the quantum noise limit. So if you do the time evolution, you can see when just look at the x-axis, then you will find that amplitude noise is reduced. So now, before we don't really know where the amplitude is. Now we have we get better information about the amplitude, but now we don't have any information about the phase anymore. So similarly, we can have amplitude squeeze light where the amplitude quadrature is reduced, or the phase squeeze light where the phase quadrature is reduced. So phase squeezing operation can be shown in here. One thing to note is that this requires the 2-photon generation and 2-photon annihilation. And when you do the equation here, S represents how much squeezing you are doing, and this angle represents which angle you are going to squeeze. So squeeze state can be represented as this. So you are squeezing the zero vacuum, and then you displace amount a certain amplitude. And when you calculate the noise of this squeeze state light with the new axis, where we align the axis to this amplitude direction, we will find that noise is reduced for the amplitude, and then the phase noise is exponentially increased. So since we have a 2-photon generation from this squeeze light, there's two different types of the squeeze light. One is that when the 2 photons are generated, they can generate into the same mode, which means that you cannot distinguish these 2 photons, and then they are into the same frequency, same polarization, everything is same. In this case, we call it single mode squeeze light. In picture, you can see 2 photons here, but in real life, you cannot distinguish this photon. But the other case is the 2-mode squeeze light, where you can distinguish these 2 different photons. In this case, they can be different direction, or they can be different frequency or different polarization. So when you can distinguish these 2 photons, this is called 2-mode squeeze light. So 2-mode squeeze light can be represented as similarly like operation of A and B. So before we have an A square, but now we have a new mode B. So now we are having an A and B generated at the same time. And 2-mode squeeze state can be represented as moving the vacuum state, actually squeeze the vacuum state and moving the squeeze vacuum to the certain amplitude. As you can see that we are generating into the 2 photons, so squeezing is not into a single photon because of the amplification. Actually, when you just measure 1 photon here or 1 mode here, you will see the more noise, more than the quantum noise limit when you just look at one of the quadrature. In order to look at the squeezing property, the quantum property, we need to actually look at the force field together. So when you look at the force field, like for example, we define the new quadrature, x sum, so amplitude sum different, or phase sum and different, you will see the squeezing property. In this case, when you calculate it, you will find that x difference, which means amplitude difference, is the squeezing property, while on also the phase sum, you will see the squeezing property. And this is physically, we have a two-photon generation, which means that the intensity of the two optical modes are correlated to each other. So then since their fluctuations are correlated, we need to look at the subtraction of this field to see the reduced noise property. That's why we see the subtraction of the amplitude, we see the reduced noise property, and phase sum, we see the reduced noise property. So since we talk about what is quantum light and what's the mathematical description of the quantum light, we want to generate an experiment. And if you want to generate the experiment, we need to find a source that can generate the two photons at the same time. So to find the material, we need to study some of the material property. So before laser was invented, people work with a small light, small electric field, and they can kind of treat all the metal with a linear response. So if, let's say you put one electric field, one photon, then one photon will be emitted, or one photon is absorbed. If you put five photon will emitted, five photon will absorbed. So then this response will be linearly happen. But as the laser is invented, now we access a high electric field. This can saturate the process. And while it's saturated, we cannot really use the linear model anymore. That's why we need to expand our term to second order and third order. So we can use actually second order or third order to generate the squeezed light, because the second order and third order allow us to generate the two photon and three photon generation. So this is one of the second order process called frequency difference generation. And you can see that one of the electric field is absorbed, while the two field is emitted. And in this process, we are driving the field with omega-2. So then omega-2 will be amplified while the new field is generated. In this case, in the quantum mechanics, we don't really need this driving field because this can be happen spontaneously. So when that happens spontaneously, two photons generate at the same time. So this is the good way to generate the squeeze light, and this is called spontaneous parametric down conversion. And for this process, usually happen in the BBO crystal and KTP crystal. And generally, most of the common way to generate the squeeze light is the KTP crystal. People use the cavity and put using the crystal inside of the cavity and use that to generate the most squeeze light in the world. And they were able to generate about 15 dB of squeezing, which corresponding to about 97% noise reduction from the quantum noise limit. In our lab, we are using atom to generate the squeezed light. And in atomic system, this is slightly different with the crystal, because atom does not really see the direction, which means that if light is coming from the left to right, or right to left, or bottom to up, light doesn't really see this difference. So they have an inversion symmetry. Because of that, the second order will disappear, and the next dominant term is the third order process. So in the third order process, we are using the Fourier mixing process to generate the squeezed light. You can see that now two photon is absorbed, while the two photon is emitted. In here, you can see that omega-3 is modulating the process, and then new photon is generated for the omega-4. In this case, the omega-3 and omega-4 is generated together. We can see the squeezing property. And in experiment, this is experiment setup that how we generate the squeezed light. This is an energy level diagram, which is slightly different with the previous one. But if you look at these two photon, this is how we get absorbed. And then two probe and conjugate is generated simultaneously. So even though it looks a little bit different, it's effectively the same picture. And then in experiment, we are putting these two photon inside the one optical beam. So from the one optical beam, two photons get absorbed, while the two photons is generated. So when you look at the probe beam will be amplified while the conjugate is generated. Since they are generated together, their fluctuation is correlated. So when you just measure the intensity and difference of intensity, we can see the noise reduction. And in our lab, we were able to generate about 9 dB of squeezing, which is about 90% noise reduction from the quantum noise limit. So there's a two parameter which is important in our experiment, which is one photon detuning, which is a detuning from the ground state to excited how far away from our pump beam. And then this is important because let's say if you do too far away from the resonant transition, then we start decouple with the atomic transition, so we don't really see optimum Fourier mixing process. So we need to get a little bit closer to the atomic transition. However, if we are getting too close to the atomic resonance, then we start having absorption and other effects such as Kerr effect and higher order effects are happening. That's why we don't really see the good Fourier mixing process. That's why we need to optimize some of the one photon detuning. In our case, we optimize at 800 megahertz away from the resonance, and that's why one photon detuning is important in our Fourier mixing process. The other process which is important is two photon detuning. The two photon detuning is the detuning of two transitions, so that pump and probe is closing the loop and then connecting these two ground states. Since the Fourier mixing is rely on the atomic coherence of these two ground states, that's why these two photon process is important. And when they are far away, then we are not really getting help by the atomic coherence. That's why you need to be resonant and closer to the two photon resonances. In here, this is more sensitive than one photon detuning. So usually one photon detuning, you can go gigahertz or 100 megahertz. But two photon detuning, if you go more than 100 megahertz, we cannot really see the optimum Fourier mixing anymore. So we talk about how we generate in our lab squeeze light, and my work is focusing on the atomic resonance squeeze light. And we are doing this because atomic research already show extreme sensitivity. And to do that, we need to generate resonance squeeze light. So there's a lot of work, because of this interest, there's a lot of work already tried to generate the atomic resonance squeeze light. So as I mentioned, the crystal is a good source to generate the squeeze light. So there are some of the work trying to generate atomic resonance squeeze light using the crystal system. For example, they put the KTP crystal inside the cavity, and they were able to generate the squeeze light. But when they try to get to the atomic resonance, it's difficult because they need to pump the crystal with the UV light, and there's a lot of loss inside of the crystal. Despite the difficulties, people still have been able to generate about 5 dB and 3 dB of squeeze light in the rubidium and cesium resonances. In our case, we are using the atom to generate the squeeze light. And atom is actually it's more natural way to generate the atomic resonance squeeze light, because atoms are rely on the atomic transition, so that's why already light is already near the resonance, and also the light generated from the atom is narrow band, so we can easily interact with atomic system. So for the atomic system, people usually use the polarization self-rotation and Fourier mixing process to generate the squeeze light. But when they try to get close to the atomic resonance, this is a little bit challenging, because absorption start dominating the process, we cannot really generate the squeeze light. Despite the difficulty in our lab, in my work, we generate the two-mode and single-mode squeeze light, which is resonant with the rubidium transition. And I will talk about a little bit more detail about my work here. So there's two different cases for the two-mode squeeze light. When one of the light, because we are generating the two photons at the same time, if the one of the field is resonant with the atomic system, or the other one is that both fields are resonant with the atomic system. In this case, we call it singly resonant two-mode squeeze light, and the second case, we call it doubly resonant two-mode squeeze light. And for the singly resonant case, I will talk about this one first. So we talk about one photon detuning. So one of the easy way to think of to generate resonant light is we just tune our one photon detuning beyond resonance. So then our probe beam is resonant with the atomic resonance transition. However, the problem is that, as I mentioned, that because of the absorption, we start dominating all the process, we cannot really generate resonant light. So in order to do that, we actually take advantage of the rubidium isotope. Because rubidium have a friend called rubidium-87, they have a very similar energy level structure. That's why we can actually tune our process and fix our one photon detuning to the one of the transition here. So then we can generate the resonance squeeze light of the F2 to F2 transition. And also if we tune a little bit more, we can generate the conjugate is resonant with F1 to F1 transition. So here, we are using 85 as a source to generate the squeeze light, and our light is resonant with 87 atom. So here's the explain of the setup. Here is the Fourier mixing process, and here we have a saturation absorption spectroscopy. And we put small beam, we take a small part of the beam before the Fourier mixing and put it into the saturation absorption spectroscopy. This allows us to measure the absolute frequency of the probe. And after the generation of the Fourier mixing of squeeze light, we actually take a look at the bin note between the probe and conjugate to extract the frequency between the difference between the probe and conjugate. So we know both frequency information of the probe and conjugate. So here, this is the saturation absorption spectroscopy spectrum, and this is 87 and 85 peak here. X-axis is the detuning from the transition. So we are actually interested in F2 to F2 transition of the rubidium A7, and F1 to F1 transition of the rubidium A7. And this y-axis is a normalized transmission. So we are normalizing by the input power. So if you have more than one, which means that you have a gain of the process, you have some point mixing process generate a new light. So then if you do the point mixing, you can see our probe beam have a gain at the one of the transition, and the conjugate beam also have a gain of the transition here. And when you measure, like, let's say we fix the one of the light, and then measure the frequency between the probe and conjugate, we find about 6.104 gigahertz away. So then we need to tune one photon detuning, so that we can also resonate with F1 to F1 transition. In this case, we were able to measure 6.3 dB of squeezing for the probe being on resonant, and 6.2 dB of squeezing when the conjugate is resonant. And you can see that this is slightly lower than the 9 dB of squeezing at the beginning, because that we are fixing one photon detuning to the specific transition. Now it's not efficient anymore. That's why we got a little bit lower squeezing than 9 dB of squeezing. So now we generate a singly resonant squeeze light. If you want to generate doubly resonant squeeze light, we can do kind of similar way that first we fix one photon detuning, so one of the transition of the rubidium A7, and then using the two photon detuning to connect detune so that we can also make the conjugate is resonant to the another transition. In this case, the two photon detuning is a frequency difference between these two energy levels. So then we have to fix that there, so that's also another limitation there. But we are doing this one because there's interest to generate the two resonant two-mode squeeze light, because when both beams are atomic resonant, then what we can do is these two beams have a quantum correlation in charge quantum property, so we can transfer this quantum property to two remote atomic systems. So then we can actually connect these two remote atomic systems using the resonant, doubly resonant two-mode squeeze light. When you do that, we can see that our process gain is much reduced, because now we are fixing one photon and two photons. That's why we are getting much lower efficiency of the point mixing process. But we're still able to generate some of the gain at the two different transitions, and frequency difference between these two is 6.02 gigahertz. And in this case, we were able to generate the doubly resonant two-mode squeeze light. We got about 3.9 dB of squeezing, which I mentioned that because now we are constrained with the two different parameters, that's why we got much lower than this previous squeeze light. So good thing about our singly resonant squeeze light is we were able to generate a large amount of squeezing, which is 6.2 dB of squeezing. So we can actually use this process to generate single mode squeeze light. So if you just measure one of the beam and then transfer this property to the other beam, we can actually generate a single mode squeeze light. And this is important because the LIGO and the other experiment, they are using the single mode squeeze light. That's why there's a lot of interest to generate a single mode squeeze light. So here, this is technique called feedforward technique. So first, we start with the correlated light, that we have a two-mode squeeze light probe and conjugate that are quantumly correlated to each other. And since their intensities are correlated to each other, if you measure one of the intensity here, and then using that intensity to modulate the another probe beam. So let's say because their intensities are correlated, I know that probe beam without even measuring. When my conjugate is high, then my probe beam intensity will be high, so we can kind of reduce that. When the intensity is low, then I know that conjugate beam it is low, so we can increase that, so that we can actively feed forward our information from the conjugate to reduce the fluctuation of the probe beam. In this case, the probe beam noise can be reduced, and then this can be reduced below the quantum noise limit, because our beam is correlated below the quantum noise limit. So here is our experimental setup. So then here is the point mixing process, and then a saturation absorption spectroscopy to measure the frequency of the light. And then here is the feedforward technique. You can see that we are introducing some of the optical delay, because our feedforward technique, the electronics, are introducing some of the electronical delay, so we need to compensate that. That's why we put the optical delay in here. So here's our experiment, the result. That this is our resonant case for the point mixing process. You can see that we have a single beam is much higher than quantum noise limit. As I mentioned that because when you just look at the single beam from the two-mode squeeze light, because it's amplified and there's a correlation between the two beam, we don't really see the reduced noise property for the single beam, or we have a more noise. But after the feed forward, you will actually find that noise is reduced below the quantum noise limit. The red line is the prediction, and then black line is our experimental result. You can see that we got very close to the theoretical prediction, which is 3 dB, and we got about 2.9 dB of squeezing. For the resonant case, where the probe beam is resonant to the one of the transition of the Rubidium 87, we find about 2.1 dB of squeezing below the quantum noise limit. So we were able to generate the singly resonant two-mode squeeze light, doubly resonant two-mode squeeze light, and resonant single-mode squeeze light. So there's some of the limitation, as I mentioned. That first, for the singly resonant squeeze light, we are fixing one photon detuning. We are not really operating at the optimum place. For the two doubly resonant case, now even we are worse. We are operating into the two constraint. That's why we don't really get the good squeezing. And another limitation is when you try to generate other transition, this technique does not really allow us to generate other transition of the Rubidium 87 or Rubidium 85. So that's why we need to find another way to extend our applicability to resonate with the other transition of the Rubidium atom. So when you look at what we have here, we have a 9 dB of squeezing, which is 800 megahertz away from the one of the transition, and also 6.3 dB of squeezing, which is about 860 megahertz away from the one of the transition. So if we can increase the frequency tunability by 800 megahertz, then we should be able to generate another resonant squeeze light for the different transition. So to do that, we introduce atomic dressing. So let's say if you have an atom and you dress the you apply the external field, such as electric field, magnetic field, or even optical field, then effectively the energy level structure will shift, and this is called atomic dressing. And if we find some of the good dressing, such that we can hold our energy level structure and shift this one together, then our probe beam can be resonant with without dressed atomic system. So in this case, there are many different ways to dress the atomic system. For example, one way is magnetic field, called Zeeman shift, where the magnetic sublevels are splitting each other. But problem of the Zeeman shift is that now it's spreading, that it actually introduces a broadening of the absorption. That's why we cannot really use this effect. The other process is called AC stock shift. We introduce optical field, and in this case, you can see that nicely they are moving together in certain configuration. But problem is that now we are introducing high optical field, like high intensity optical field. Then since when mixing is also reliant on optical field, this can also mix each other and have a higher order effect. Actually, Kit Leonard in our lab is working on this to enhance the foil mixing process, but in here we are not going to talk about it. So what we use is DC stock shift, that we apply electric field to shift the energy level structure. In this case, in the D1 line of the rubidium, all the energy levels are shifted together. That's why we are using the DC stock shift to do the frequency shift of the foil mixing process. So to do that, we need to have some kind of plate and apply the electric field and put the rubidium atom inside and do the foil mixing process in there. And if you can do it, if you can apply high electric field, then we can move this energy level together, so then our probe beam can be resonant with the rubidium 85. But to do that, we require a high electric field. So for example, if you try to do it in our setup, that we 1.5 millimeter separation between two plates, we have to apply about 17 kilovolt to shift 800 megahertz. And that's quite a lot of electric field, so that's why don't try at home. It is dangerous. And because of its high electric field, we have to iterate our process, the design of the chamber. Because first we try to buy some of the cell, but the problem is that this is very sharp. Every edges are very sharp. Electric fields are condensed there and start arcing and discharge. That's why we are going to the next step, and this is the final design of our chamber. And you can see that all the plate is really smooth, and we are holding this plate with the maple insulator. And here, with the feed through, we are applying the electric field, and then the other plate is grounded and chamber is grounded. Still, we are limited by some of the discharge because we cannot really make it smooth anymore. So for example, if you don't treat the surface nicely, then you will start seeing the arcing. So you arc and generate the electromagnetic pulse. And this is really critical in our lab because it start destroy other devices such as a laser. That's why this is quite, you need to make sure that you don't really arc in the lab. So don't try at the lab neither. And also, we also have another process, another discharge that if the vacuum is contaminated, then you start ionize the discontamination, and we make a $10,000 light lamp. So that's why also we need to control the contamination. We are able to fix the contamination, but we are still limited by the arcing a little bit. So here is the experimental setup. So this is a Boy mixing process with the DC stock shift, and then saturation absorption spectroscopy. And this is our measurement. That this is a normalized transmission, and this is for mixing spectrum. And we are here, now we don't really apply any electric field, but as we apply electric field, you can see the shift of the transmission. So then we can see that this is 0, we are getting close to the resonant transition, and then you can see that there's a yellow and blue. I just want to trace that peak of the transmission and also tail of the mixing transmission. And when you plot how much we got shift, you can see that red line is a prediction. So we can see that it's following the prediction for the blue point, but the orange point is not following the blue prediction. This is because that when you look at the plate, this is chamber. So when you have a look at these two plates, you have some of the room here. This is not really participating in the DC star shift because there's some place that it's not really uniformly electric field is applied right before the window. That's why this introduces some of the residual absorption. That's why this will start killing the peak of the Boy mixing process. That's why we are seeing some of the divergent effect here. So this is a squeezing measurement. There we got about 3.8 dB of squeezing at the maximum. And then this is a frequency detune. So with the electric field, we were able to see about 600 megahertz shift from the peak to peak. And also when you look at here, within the uncertainty, we were able to get small dB of squeezing. So in conclusion, we were able to generate a small dB of squeezing in the small dB of squeezing at the resonant case, and we were able to shift the 3.8 dB of squeezing. And with the electric field, the squeezing is still preserved, but we still limited by the arcing, so we cannot really increase any more field because it starts discharge, we cannot apply high electric field. So we were able to generate the resonant single light and resonant doubly, resonant case, two-mode light, and also we can even shift the cases. So now what we want to do is try to expand this applicability to the quantum information science. Before we generate a single mode and two mode, if we can generate a multi-mode light, let's say we generate 5 and 6 different modes, then this will be beneficial for the quantum networking. For example, there's a 2-atomic system, let's say 2-atomic sensor or 3-atomic sensor. We can use the just normal light to do it, but if you use the multi-mode squeeze light, then we can actually take advantage of the reduced noise property to actually enhance the distributed quantum sensor or even making a quantum network. So there are many efforts to generate the multi-mode squeeze light. One way is using the single mode squeeze light put into the beam splitter and adding the beam splitter array to extend the number of the mode. And the other case is adding the Boy mixing process called parameter amplifier, adding more process to generate a multi-mode squeeze light. But as you can see that this process is limited because as we introduce more optical elements, this will add a cumulative loss into the system. So if you want to generate like 10, 20, then you require like 10, 20 beam splitters or 10, 20 step of the losses here. So what we do is actually try to get rid of these losses, cumulative loss, by our proposal here. So this is not experimentally work, this is more theoretical proposal. So here we start with a 4-mode case and we will show how we can extend it to the multi-mode squeeze light. The 4-mode case, we use the first stage of the Boy mixing process to connect these two dots between A and B and C and D. After that, we switch the B and D, and then we put it into the second stage of the Boy mixing process to complete the loop here. In this case, we can generate the 4-mode squeeze light, and we can easily scale up to the 6-mode and 8-mode case. And this case, you can see that we rely on the only 2 states. That's why we are only limited by 2 losses. So one of the good thing about our experiment is that we theoretically show that this have some quantity called genuine multipartite entanglement, But another important thing about our proposal is this is experimentally really simple. So for example, we prepare the two-fold mixing process with the dual prism here. And each beam have a 4 different optical mode, so they are just specially separated to each other. We can generate by the meters and we can generate by the SLM. In this case, we can have a 4 different optical mode into the one beam. And when they go into the first Fourier mixing process, they will connect each other for when they are meeting each other. So you can see A and A, B and B, C and C are connected. And we propagate a little bit more. And then here, dual prism will switch this beam. And then after that, when they connect them again, you can see that they are completing the loop here. So this is effectively same thing as this complicated system here, just by compact two Fourier mixing process. So in conclusion, that we were able to show that just the resonance squeeze light to way to expand it to the multimode quantum light to apply for the quantum information science. So in conclusion, we are talking about how we generate the squeeze light and how in our lab generate the atomic resonant light, and our proposal to the multimode squeeze light. So the enhancement of the optical interferometer, now in our lab, we extend it to the commercial sensors and also extend it to atomic sensors. So in our lab, we are enhancing the applicability of the quantum light, and hopefully that this will be foundation of the quantum technology 10 years and 20 years later. So before I close, this is my publication and some of the papers and patterns that we are working on, and some of the invited talk and then conference talk, and then the poster presentation here. All the work cannot be done by myself, so I want to acknowledge some of the people here. Thank you.